So, very welcome to a seminar for Researchers Desk this Wednesday, March 5. Today we will listen to Frederik Schenk at Stockholm University at the Department of Geological Sciences, talking with us about the North Atlantic currents and with a focus then on the stability of the AMOC. So with this, Frederik, please, the floor is yours.
Thank you. I'll share my screen. Yep, should be full screen now, I guess.
Looks fine.
Okay. Yeah, then thanks everyone for joining and for asking me again about, giving a talk about the Gulf Stream system, or the AMOC, how we say that as scientists. And the reason to talk about that topic is because it's important, but also because it's a lot in the media. And I think there's some kind of confusion sometimes going on what the media says and what actually the science says. So I will mix the talk today, talking a bit about the science, but also about what people talk in the media. And so it's a bit a mix of science and media. And yeah, personally, I work on AMOC impacts. So I do not currently, at least, not study the stability of AMOC. That's done by other colleagues. So I do paleoclimate research with climate models and reconstructions to see what actually happens when the AMOC collapses. From that impacts, you can also sometimes reconstruct the AMOC itself. So it's kind of a circular problem. And the comparison with climate models and proxy is, of course, very important because we do not know much about the North Atlantic current from observations. So if we want to really test climate models with observations, we need to do that in the past, also on longer timescales. And yes, I'm at the geology department in Stockholm, and currently I'm a visiting scientist in Helsinki until the summer. And I'm also one of the co-leaders of the research area Past Climates at the Bolin Centre. So now I need to go to the next slide. Doesn't work. No, it does. So yeah, before we start, because we are a mixed audience in the media, you often hear Gulf Stream. So whenever we or the media says Gulf Stream, in the end, we actually mean the AMOC, because the Gulf Stream itself is only this very small part here which comes out from the Gulf of Mexico here. And that's actually wind driven. So even if the AMOC, so the whole system collapses, the Gulf Stream will still continue. It will get a bit weaker, but it will continue. So the Gulf Stream itself cannot collapse. And the continuation of the Gulf Stream is shown here in red, which is the North Atlantic current or North Atlantic drift. And that's also partly wind driven. But it's also driven by the density of ocean water, because whatever you push northwards in terms of warm and salty water has to return to the south. And currently that's done by that the water gets more dense and cold, and then it sinks to the deep. That's shown here in blue. And then it returns to the southern hemisphere. And this whole overturning circulation, that's called the AMOC. And what it means for the northern hemisphere and also Europe, it means that we get a net northward oceanic heat transport. So our climate gets warmer than it would be otherwise. And also we get more moisture in all seasons. So because warmer water also evaporates more, and then we get more rain. And the strength of this AMOC depends on the density. So that's defined by salinity and temperature. And it partly also is driven by the wind. So even if salinity and temperature are such that the AMOC collapses, a small part of AMOC would continue because the wind doesn't collapse. And in the past, we know that this deep water formation, which drives the AMOC to extend to the north, can be shut down or slowed down, and that typically has severe consequences. The problem with studying the AMOC is that we have only very little direct observations. So we have rapid measurements, which is shown here as this line around 16.5 degrees north, where we really measure the through flow which goes north. And based on that data for 2004 till 2022, we have a small negative decline of AMOC, but this is very uncertain because the variability is high and the number is not small if it would continue like that. So that's a bit the concern. Small trends on short time scales lead to very big changes on longer time scales. And at some point, this weakening could actually then mean a collapse. And it's very common actually that the AMOC is unstable, at least during cold periods in ice ages. You see here an example from the Greenland ice record. These are oxygen 18 isotopes, and they track temperature and moisture changes. And you see here this ups and downs on a time scale of 100,000 years. And the downward excursions typically imply a weak or collapsed AMOC. And the upward excursions are a fast recovery of AMOC. And you see that it's always going back and forth. And these abrupt warming periods are called Darmstadt-Oeschger events, and rapid cooling events, at least the major ones, are called Heinrich events. And Heinrich events are well known in the North Atlantic sediments because at least some of them are related to discharge of icebergs, which break up from ice sheets, and they carry some small sediments with them. And when the icebergs melt in the Atlantic, this small debris sinks to the ocean, and then we can see, okay, during that time we had icebergs floating on the Atlantic. And you see here on the right side also a small excursion, that's the 8.2 event. So it means that the AMOC can also be unstable in the warm climate, but it's less dramatic. And there's some weak evidence that the AMOC can also struggle in warmer climates. Here's an example from the last interglacial around 127,000 years ago. And what you see here in the figures from ongoing publication we work on the left side, you see annual mean temperatures for the black line. So this is a pollen-based temperature reconstruction from northern Finland in Sokli. And the blue line, which is shown on the right axis, that's an AMOC proxy from the Atlantic. And you see that they nicely align both this Tunturi event, which is an abrupt AMOC shift in the early last interglacial, and you see here that it nicely correlates between the marine record and the temperature in Sokli. And in addition to this abrupt event, you also see that the long-term trends and the low-frequent variability of the blue and the black line, they co-vary. So that is a clear proof that on long time scales, not only the abrupt climate shifts of AMOC matter for the European climate, especially Northern European climate, but also the long-term trends. So we always talk about AMOC collapse, but it is also important if there's a change in long term because that affects temperature and moisture as well. Yes, and so AMOC or the Gulf Stream is very popular in the media. And that makes also sense in Scandinavia because if there's an issue with AMOC, Scandinavia is basically hit the most, at least in terms of temperature. A key problem we have in this media and science debate is that we simply don't have enough data to be very confident about what we say. And we are also unsure about if we should trust the climate models. So whatever papers we have, we always are somewhat uncertain if we can rely on it. So we need more data and more research, no matter how good a paper or research is done. And that also leads to the fact that climate scientists, of course, disagree. And what is maybe unusual is that they also sometimes disagree in the public. So. But that's not a bad thing in general. It's just we need to deal with it. And maybe for the public, as non-experts, it's sometimes difficult to follow what exactly the debate is. So 2 years ago, I gave almost exactly 2 years ago, I gave a talk already at Researcher's Desk. It's more or less the same question as now. But there are now many more papers. And I think what has happened in these 2 years is maybe phase one was 2 years, 3 years ago. So there were papers also from paleoclimate on longer time scales, which indicate that the AMOC has already been slowing down since quite a while. And the phase 2 is that then people start to use climate models and also use statistics based on this proxy data or observational data to identify if we can actually say if we are getting closer to a tipping point. And some of these studies find that this is the case. And phase 3 is basically that a lot of other scientists then disagree both with the evidence and also the theory in the methods. And that's where we are currently. So you get one study which shows we are getting closer to the tipping point, and the other study says actually we don't have enough evidence to say that. And I think that will also continue like that. And there were some open statements also done here. Two examples. One is from the German Meteorological Society, and one was an open letter by climate scientists to the Nordic Council. That was both last year, and they look like, if you read them, that they actually say the opposite, but if you are careful, they actually kind of agree on the main message. The main message is that we have a problem. But there's a disagreement about talking about tipping points. So on the right side, you see the example that the string of scientific studies in the last 2 years suggests that the risk of reaching a tipping point or AMOC collapse has been strongly underestimated. And German society basically says, well, we cannot really say that. And so the Meteorological Society is more conservative, so they are concerned that people abuse or misuse the word of tipping points, because we don't know if the AMOC will have a tipping point and what does tipping point actually mean. And so they think that it's alarmism to use that. They mainly refer to the IPCC report, but they actually ignore the most recent papers. I'm quite sure they know the papers, but they do not mention it. But if you read the conclusion, they actually highlight that even without these tipping points, that climate change will have drastic impacts. And the open letter more refers to the most recent papers, and they say that the IPCC underestimates the risk of AMOC collapse and tipping points. And I think a lot of scientists maybe are between these two positions. So they are concerned, but maybe not alarmistic. And no matter what you think, in both cases, we need to fix the climate problem, because it's the only way how we can avoid an AMOC collapse or AMOC decline. And another controversy is that these limited observations or proxies which we have, they do not agree with the climate models for these periods. So the question is a bit, is the AMOC too stable in climate models? That's a very difficult question. And so there was one study by Ditlevsen, for example. They used statistical methods based on a simplified AMOC index, which uses observations. And they found that we are getting quite close to a tipping point. So they would think that the AMOC might already collapse within this century, and it could already collapse by mid-century. And there's a physics-based study which simulates an AMOC collapse in a slightly more realistic way than previous climate models. And they use this simulated AMOC decline to see where we are in terms of the observed AMOC decline. And combining this, they also say that we are getting closer to this tipping point. And this physics-based study was quite big in the media in Sweden, at least. But actually not so much in terms of the tipping point or the climate simulation, but more the impacts. So the headlines was here in Swedish, basically that if that AMOC collapse will happen, it gets 20 degrees colder in Sweden. That's of course alarming. And you see that also in the right figure, the cooling here in February for an AMOC collapse. In the simulation, you get here, like 20 degrees colder in Bergen, for example, or the British Isles. And so what is different in this climate model simulations is the way how it has been done. So it's not about, we know already that it gets very cold. That's not new, but it's a more realistic forcing. and I will come to that. But the discussion in the end was not about the simulation, but about this 20 degrees cooling. And I was partly involved in that, and also my colleague Leon Shafik from Stockholm University. We were asked some days later to correct the alarmism the media has caused themselves. So we basically criticized this 20-degree cooling because the climate model simulation which they used was a pre-industrial simulation. So it did not include the rise in CO2 levels. So a huge part of the warming until now and also into the future in that climate model is completely missing. And that explains this 20 degrees cooling. So with global warming, it will be much less cooling. But that doesn't mean that the impacts are drastic. But it just means that this 20 degrees is a bit unrealistic. And my colleague, he will give a talk in June. He is also a bit doubtful if we actually can say that the AMOC is slowing down. He can talk more about that. And so what scientifically has happened is that in previous simulations, we typically dump in a lot of fresh water to stop the AMOC. And in a climate model simulation, that causes a freshwater shock. But that's very unrealistic because that's not what is going to happen. That's maybe something which we had in the past when proglacial lakes, ice-dammed lakes broke out and then flushed the Atlantic. That's a freshwater shock, but that's not what we expect for the future. In the future, the freshwater is more gradual. And in this simulation, they for the first time did that in a very realistic way. So you see here in the figure, the time axis, this is model years, so it's not calendar years. And you see that it's over 2,500 years of model simulation. And at the top, you see here these numbers in 0.1 Sverdrup, 0.2 Sverdrup. That's the amount of fresh water they add. So it's very slowly adding fresh water very gradually. And then check what the climate model does. So the AMOC here in black doesn't respond much to it for almost 1,000 years, and then it starts to slow down for another 500 years. And although you only add very small additional fresh water, at some point the AMOC has a tipping point. And that's the first time that this has been shown in such a realistic way. And yes, that basically means that climate models can simulate AMOC tipping points, but we don't know how much fresh water we actually would need for that. And the study is still theoretical because, as I mentioned, the CO2 warming is not included. So the warming would actually maybe shorten the period until you have a tipping point, because the warming itself already weakens the AMOC in addition to freshwater, but it would also balance some of the cooling. And the freshwater distribution is also rather theoretical. That's shown here on this globe with this minus FH and plus FH. That's the freshwater is taken out from the South Atlantic or the tropics. And then this amount is put as freshwater into the Atlantic. So the balance is 0, but the Atlantic gets more fresh. And that's not exactly what would happen in the future. In the future, the freshwater would rather come from Greenland ice melt and more precipitation. So that's a bit theoretical, but it shows that AMOC tipping points are real even in complex models. And the media didn't care about this. Of course, they care about impacts, which of course makes sense. And I think that was the nice thing this study did. In addition, they also showed here climate diagrams for precipitation changes in blue and for basically AMOC collapse in blue, and in reddish color, it's before the collapse. In addition, they show the temperature changes as lines. And then you see that in Northern Europe or in Europe, you see a big winter cooling. And in the Amazon region, you see for precipitation that the red and the blue bars strongly disagree. So that means for AMOC collapse, there might also be a collapse of the monsoon systems. That's not only in Amazon, it's also true for Southeast Asia, where I, for example, work on for paleoclimate. And this is something we know from geological evidence. If the AMOC collapses, there is also a collapse in tropical rainforest. So the model also shows that. And this cooling effect was mainly the message in the media. And yes, so this 20 degrees cooling is maybe too much because CO2 is missing here. But it reminds me of the work we do with paleoclimate simulations. And I checked actually with a PhD student if we can confirm this around 20 degrees cooling, which is shown here in the simulation. For example, yeah, you see it here in the time series in the reddish color for Reykjavik in Iceland. That's of course directly affected by the AMOC collapse, but also Bergen in Norway. So they will directly be affected by the AMOC collapse and mainly also by the cooling from sea ice. And if you go more on continental sites like Madrid or so, then the cooling is weaker. And if we go for the last AMOC collapse event, which we had around 12,000 years ago, that's called the Younger Dryas. A PhD student, Liva Trasune here in Helsinki University, she did climate reconstructions for the Baltic states. And on the left side, you see January temperature reconstructions. First of all, that's still the end of the ice age, so it's 23 degrees colder than today. But you see here in around, for the Allerød, around 13,000 compared to the Younger Dryas around 12,000, that this AMOC collapse, which we had at that time, was causing a cooling of 15 degrees. So that's relatively close to what the climate model suggests for the pre-industrial. The difference between the modern and future climate is, of course, that there's CO2 compensating, while in the pre-industrial and in the past there's no CO2 compensating. So I would expect that in the future this cooling would be somewhat less. But what is maybe a bad thing for the future is that the cooling might not be the biggest problem, but it gets actually very dry. And there's also a study from quite some time ago to look at what happens if the AMOC collapses, but the CO2 continues to increase. So that's a bit more realistic scenario, but the model is a bit more simple than we have it now. And on the left, you see the global mean temperature with the A1B scenario. So that's the SSP 5 scenario. So more or less, if you continue like that, that's the warming scenario. And the blue one is if you collapse the AMOC completely at year 2000, but you continue to increase CO2, then you see that you have a cooling effect, but it quickly lines up again with the warming trend. On the left, on the right side, you see the cooling map, which we have at the AMOC collapse after 15 years. So that's consistent with what I have been showing before, but it's already here much less. It's not 20 degrees, but it's only around 5 to 10 degrees. And if you go 100 years later, the CO2 warming kicks in. So even though the AMOC is still collapsed or weak, the global warming takes over. So it means that the AMOC collapse doesn't save us from global warming. It only makes it worse. And the offset in the warming for Europe or the North Atlantic is around 40 years. So after 40 years of AMOC collapse, the CO2 increase will catch up. So that's about AMOC CO2, yes or no. And what is coming up now, I think already one paper is out, but there will be more. Misunderstandings also in science and media. What do we actually mean with an AMOC collapse? And there was now a study from some days ago in Nature, which has this, in my opinion, slightly misleading title. It says continued Atlantic overturning circulation even under climate extremes. So what they do in that model simulations is that they use 4 times CO2 levels and compare 34 models and check how the AMOC behaves. And what they find is that all models show a strong decline in AMOC, but it never collapses. And they really focus on this aspect that it does not fully collapse. And they explore why that is. So they find that the upwelling in the Southern Ocean, so that's around the Antarctica, is driven by Southern Ocean winds. And these winds don't stop with global warming, and they also don't stop with an AMOC weakening. So they basically sustain the AMOC because they upwell water from the deep ocean And every water that comes up in the Southern Ocean has to sink down somewhere else on the globe. And currently, this sinking is done in the North Atlantic, and that is driving the AMOC. So if you weaken the AMOC in the North Atlantic, you still need to balance the upwelling from the Southern Hemisphere. And that's an argument which they use, that the AMOC cannot fully collapse because you still need to have deep water formation. And based on that, they argue that there are stabilizing mechanisms for AMOC, so the AMOC will not fully collapse. And for me, and I also asked also some colleagues, it's a bit surprising statement, because when we modelers talk about AMOC collapse, we only talk about the collapse in terms of this thermohaline effect, so the deep water formation in the North Atlantic. We never actually mean that the wind-driven AMOC will collapse. So I think that's a bit a misunderstanding. And that also means that most climate modelers say AMOC collapse, but it does not mean that there's zero transport in the AMOC. It just means that it's very weak. And I think that's kind of very misleading. And some people are celebrating now the AMOC is not collapsing, but that's actually not true. And the explanation here, that's already very simplified, but you see how complex that system is from that study in Nature. This shows here on the left, for example, for the present day, how the overturning circulation works for the AMOC. So that's in the Atlantic. And there's a very weak circulation also in the Pacific, but there's no real overturning in the Pacific. And along the southern part around Antarctica, you have these strong westerly winds, and they always lead to water coming up from the deep ocean. So the water turns from green to yellow, that's upwelling. And this water is then transported, for example, in the North Atlantic, where it gets cold and dense, and then it sinks to the deep and goes back to the, to the Antarctica. So that's how it works today. And if you now have global warming and the AMOC gets weaker, you still have this westerly winds in the southern hemisphere. And some models start to have a slight PMOC. So that's the same thing as AMOC, just in the Pacific. But this PMOC is not able to get as much deep water formation as the AMOC. And that's an argument that they say, as long as these winds are blowing and water's upwelling in the southern hemisphere, the AMOC cannot collapse. And the problem with that study, that's very briefly mentioned but not explored, is that there would be, in theory, some other mechanisms which can remove water from the surface, and that is through ocean mesoscale ocean eddies. So they cause mixing of the ocean. And they could actually increase with global warming and compensate some of this upwelling. So it could still be that the AMOC can fully collapse if these eddies compensate some of that. But that's something you need very expensive models for. They need to be very high resolution, and we do not have many of these yet. So in the end, it means there are stabilizing effects, which is wind, which has been known, but here they quantify it. But we need better models to actually say how much that is a stabilizing effect. And the last example, which I don't go into detail, is the burst controversy. So that's maybe how science works these days. I think that's also a good thing. So Nicholas Burst published a paper about early warning signals in observations. And then he got a reply by Chen and Tung. They wrote that, well, for these observations, we have actually lacking evidence. And then Nicholas Burst was allowed to reply to that. And I think some of the concerns he could resolve, but some he couldn't. And the key issues of all these studies is that in order to detect these early warning signals, you use some statistical methods. And for that, you need very long data, at least 120 years. And for a lot of areas in the ocean, we do not have that, or not in good quality. And the argument of Chen and Tung is that the data quality is actually causing some of these early warning signals. So not the climate, but the poor data quality. And I think Nicholas Burst could show that in most cases, the data quality is not the problem, but still the time scale is very short. And another criticism, I think, which also Leon Chafik in June will talk more about on researchers' desk, is a bit, they need to use a simplified AMOC index. And some people say that this AMOC index is not very useful. So all the statistics which you do for early warning signals with this index are kind of doubtful because it's not fully clear if it's actually representing the AMOC in a good enough way. So that's more or less some examples. And concluding remarks is maybe that there are many papers with mixed evidence whether there is a weakening of AMOC or not. I think overall you can say there's a tendency that there might be definitely a weakening, but we are not sure how much. And models in principle can simulate AMOC, but it's unclear if they are too stable. And something which is completely missing currently is actually the meltwater from Greenland ice sheet. That's typically not included in climate models, but in the past, that's actually the main source which weakens the AMOC, so the meltwater from ice sheets. So what all we talk here about could be actually worse if Greenland discharges more meltwater. And I think it's good that this last study started to check a bit also which components actually stabilize the AMOC, because that's important to take into account as well. But it's still unrealistic because to really say that you need eddy resolving models, so models at the kilometer scale. Currently, we have more 100-kilometer scale. And based on paleoclimate, I think it's important to always remember that we do not need a full AMOC collapse. Even a weakening has drastic impacts. And that goes back to this discussion about tipping points, whether the AMOC has a tipping point or if we reach a tipping point is not so important, because a strong weakening is already enough to cause huge harm. And that's from my side. And as I mentioned, Leon Shafik will talk about that. A bit more about North Atlantic anomalies and a bit about these AMOC indices, which I think is very important. And yes, I think I stop here and then I look forward to your questions. Thank you.
Thank you very much, Frederik, for a superb presentation. Very interesting.